Assalamu alaikum wa rahmatullahi wa barakatuh. I want to use this opportunity to welcome you back to the next edition of chemistry class for SS2 students of Islamic College Osogbo. Today, inshallah, as promised, we are taking off with TETRA, oxo, sulphate, cis acid, and its salts. Before we left the last class, we looked at trisulfate 6 acid, trisulfate 4 acid, and its salts. And the last thing we were looking at is sulfur 6 oxide. So I want to believe that you have gone through the notes, you have mastered the concepts, and then you have mastered the preparation of sulfur 6 oxide, but we are going to take off from here today. In order to prepare tetrasulfate 6 acid industrially, we have to go through the preparation of sulfur 4 oxide, sulfur 6 oxide, and so on like that. This method of preparing tetrasulfate 6 acid industrially is called contact process. Contact process. In contact process, sulfur is first roasted in air to obtain sulfur 4 oxide. Thus, when sulfur 4 oxide reacts with oxygen in the presence of vanadium 5 oxide catalysts, sulfur 6 oxide is produced. I told you, if you remember well, that instead of vanadium 6 oxide, we can use platinum. But vanadium 6 oxide is more commonly used because it is less expensive. Platinum is more expensive. So vanadium 6 oxide is more often used. This reaction is reversible, like you can see. Therefore, an equilibrium is often reached. If you remember the concept of chemical equilibrium, this reaction involves 2 moles of sulfur 4 oxide, 1 mole of oxygen to produce 2 moles of sulfur 6 oxide. All gases. The forward process is endothermic. Therefore, there are some factors that will favor the yield of sulfur 6 oxide, which is our focus at this stage. One, the temperature has to be lower because the forward process is exothermic rather. 2, the pressure has to be raised because the total number of moles on the right hand side is less than that of the right hand side. We mentioned this during the last class. And 3, sulfur 6 oxide has to be removed as it is formed. And that is the next stage in this process. Now, but for optimum production industrially, the temperature that is used is usually between 450 degrees Celsius and 500 degrees Celsius. So that the reaction will not be extremely slow. Because if you lower the temperature too much, the rate of reaction will be slow. Then the reaction is maintained at 1 atmospheric pressure, so that the temperature is not raised too much. Then sulfur 6 oxide is removed as it is formed by dissolving it in a concentrated tetrasulfate 6 acid. Now the question you ask me is, since our target is to produce tetrasulfate 6 acid, why not just dissolve the sulfur 6 oxide in water? Unless you see that if you dissolve sulfur 6 oxide in water, it has the tendency of giving us sulfur tetrasulfate 6 acid. So this would have been an excellent process, a very easy process, but this doesn't happen. So sulfur oxide is a very strong acid anhydride. When it dissolves in water, it generates a lot of heat that could be dangerous to handle. It can cause accidents. That's why it is not dissolved directly in water, because the reaction is extremely exothermic. So instead of dissolving it in water, sulfuric oxide is dissolved in concentrated tetrophosphoric acid. To form another liquid, which is called oleum. This is a very viscous liquid, oleum. When oleum is mixed with calculated amounts of water, more tetrophosphoric acid is produced. So from this reaction, you can see that mixing oleum with calculated amount of water will give us tetrophosphoric acid. The tetrophosphoric acid produced by this method is about 98% pure. And looking at the equation as well, you discover that 1 mole of each oleum and water is required. So when I say calculated amount, it has to be calculated in forms of moles, so that equal moles are mixed, that you don't get tetrophosphoric acid that would be too dilute. So this is how tetrophosphoric acid is produced or prepared industrially, and this process is called contact process. So next time you asked by what is the product of contact process, you would be able to say gladly that it is a tetra-sulphate 6 acid. I hope that is taken. Now, coming to the physical properties of the acid. It has a number of physical properties. Number one, it is a colorless, viscous liquid at room temperature. A colorless, viscous liquid. And when it is in concentrated form like that, it's usually called oil of future. Oil of future. Another physical property of this is that it has a density of 1.8 gram per 6 centimeter cube. That is, it is denser than water. Number 3 is that it is highly soluble in water. Or another way of saying that is that it is very miscible with water. It dissolves in water easily. Number 4 is that just like any other acid, it turns blue litmus paper red. It turns blue litmus paper red. And it has all the other properties of acids, like its dilute form having sour taste and so on like that. So these are the physical properties of tetra-sulphate 6 acid for your information. Now, coming to its chemical properties. Number 1, it has all the chemical properties associated with acids, like reacting with metals to liberate hydrogen gas, like reacting with trioxocarbonate 4 compounds to form carbon 4 oxide, like reacting with bases to form salts and water only. The only thing that you have to note is this: tetraoxosulphate acid will exhibit its acidic nature when it is in dilute form. When it is dilute form. Look at the dilute form of tetraoxosulphate acid here. Compare it with the concentrated form of tetraoxosulphate acid. You can see the difference. This looks oily and it's viscous. This is a solution of tetraoxosulphate acid. So the acidic nature is usually exhibited in dilute form, but when it is in concentrated form, it reacts otherwise, which we are going to look at as specific or peculiar properties of tetraoxosulfate 6 acid. Now, coming to the peculiar reactions of tetrasulfate 6 acid. Tetrasulfate 6 acid sometimes acts as oxidizing agent. We are all aware that when an acid reacts with metals, hydrogen gas is liberated. But that is not to be when the concentrated tetrasulfate 6 acid reacts with metals, especially metals like copper and zinc. So if you add a drop of some drops of tetrasulfate 6 acid to in concentrated form to zinc, this zinc dust, instead of liberating hydrogen gas, sulfur 4 oxide is liberated. You can see effervescence. That is the effervescence of sulfur 4 oxide. If you perceive the odor it has the odor of burning matches. The odor of burning matches. So you can see the effervescence. So this is, and that shows that the reaction is, it reacts as an oxidizing agent. And that is when you have zinc reacting with concentrated tetrasulfate 6 acid to form zinc tetrasulfate 6 and water plus sulfur 4 oxide. Now you have to take note of that. If the examiner requires you to write equation to show how zinc reacts with dilute acid, it is dilute H2SO4. It is different from writing equation to show how zinc reacts with concentrated H2SO4. If it is dilute, it will be like this. Zinc with dilute H2SO4 will give you zinc tetrasulfate 6 acid, zinc tetrasulfate 6 and hydrogen, and that's all. But because it is concentrated, it is acting as an oxidizing agent. So the hydrogen gas that is produced will be immediately oxidized to hydrogen, to water. So this is the difference. So this is dilute. This is concentrated. So you have to take note of that. And similar reactions are undergone when zinc reacts with copper. So it is, in that case too, it's also reacting as an oxidizing agent. When you have copper and tetrasulfate 6 acid concentrated, definitely copper cannot react with dilute tetrasulfate 6 acid. It can only react with concentrated, and that will give you CuSO4 plus water plus sulfur oxide. If it reacts with carbon, similar thing is observed. It will form carbon 4 oxide, water, and sulfur oxide. So in all these cases, the tetrasulfate 6 acid is acting as an oxidizing agent. So if somebody asks what is the role of tetrasulfate 6 acid in this reaction, it is not as an acid though, it is an oxidizing agent. So you have to take note of this, and you will get more of such reaction from your textbooks. So tetrasulfate 6 acid is acting as an oxidizing agent in those reactions. Another such reaction that it undergoes is when it reacts with hydrogen sulfide. When it reacts with hydrogen sulfide, it will form H2O plus sulfur plus sulfur oxide And this is why so tetrasulfate acid is not used in drying the gas. That is hydrogen sulfide. That's why hydrogen sulfide is not used as a drying agent for hydrogen sulfide, because it reacts with it. So this is one of the peculiar reactions of tetrasulfate acid when it's conjugated. Another peculiar reaction, which would form the third of the chemical property we are going to look at today, is its reaction as dehydrating agent. As a dehydrating agent. Tetraoxosulfate acid, when it is in concentrated form, also reacts as a dehydrating agent. Dehydrating agent in the sense that it removes elements of water from the compound. It removes water from the compound. For example, when sugar or any form of carbohydrate comes in contact with concentrated tetrasulfate acid, element of water is removed from it. That's 6H2O. Then you have carbon being deposited. This type of reaction, in which water is removed, you can see that this is H12O6. That is water removed from the compound. It is called a dehydrating reaction. And the role of tetrasulfate acid in this reaction is as a dehydrating agent. You can note that the reaction can also be written as the 6H12O6 plus H2SO4 to form 6 molecules of carbon plus 6 molecules of water. It's the same thing, which is also as a dehydrating agent. So this reaction and this reaction, there's no difference. So now, if you have a tetraioic acid, this is a tetraioic acid. I hope you remember. So it can also be easily dehydrated by tetrasulfate acid to form carbon 2 oxide and carbon 4 oxide. This is carbon 4 oxide. This is carbon 2 oxide. You have removed the element of water, H2O. Then you have CO and CO2 left. So that is another form of dehydration. You also have other forms of dehydration. Let me quickly tell you here that when litmus paper comes in contact with dilute tetrasulfate acid, blue litmus paper is turned to red by dilute tetrasulfate acid because that is acting as an acid. But when you put a litmus paper inside concentrated tetrasulfate acid, it will not only turn red, but it will become charred. The charring of litmus paper in concentrated tetrasulfate acid is as a result of its dehydration, and that is even why the acid is said to be corrosive, because when it comes in contact with any organic matter, it will not only react with that organic matter, it will also remove water, and when it removes water, the matter becomes charged. And that is what leads to the burning sensation that one feels when tetrasulfate acid comes in contact with the skin. So the charring of paper inside concentrated tetrasulfate acid is as a result of its dehydrating property. It's because it removes water and burns, and the process gets the substance burnt. So these are some of the chemical properties of tetrasulfate acid that we are going to look at today. Now, the next chemical property is displacement reaction. Tetrasulfate acid, H2SO4, displaces most acid from their salts. It displaces most acid from their salts, being a stronger acid than most other acids. For example, when a sort of hydrochloric acid is HCl, and an example of hydrochloric acid salt is MaCl. When it comes in contact with tetrasulfate acid, it will form Na2SO4 plus HCl. 2 moles of this. So you can see, you can use tetrasulfuric acid to prepare other acids. If you remember preparation of acid that you learned when you were in SS1, one of the methods of preparing acid is displacement of weaker acid from stronger acid using their salts. So, and this is an example. The same thing will apply to all other weak acids. Even you can get a sort of trans-identified acid. Reacting with tetrasulfuric acid, you get NaNO3 plus Na2SO4 plus HNO3 this is K2H. So this is also a displacement of weaker acid from stronger acid using the sort of weaker acid. So this is another reaction that it undergoes. Now let's quickly come to the salts. Salt of tetrasulfuric acid. So a salt of tetrasulfuric acid is produced when the hydrogen atom from the acid is partially or fully replaced. Since it is a diatomic acid, and dibasic acid rather, since it's a dibasic acid, it forms 2 types of salts, normal salt and acid salts. But when we are talking about salt of tetrasulfuric acid, we want to concentrate on the normal salts today. Now, the normal salt of tetrasulfuric acid are usually soluble in water. I always tell you, take note of these properties. All sorts of tetrasulfuric acid are soluble in water except lead 2 tetrasulfate 6 and barium tetrasulfate 6. Apart from those 2 salts, all other sorts of tetrasulfate 6 acid are soluble in water. Therefore, to prepare them, we use neutralization. All sorts of tetrasulfate acid can be prepared by neutralization, except lead 2 tetrasulfate 6 and barium tetraoxosulfate 6. So you can easily write an equation to prepare any of the tetraoxosulfate 6 salts. Except now, as for lead tetrasulfate 6 acid and lead tetrasulfate 6 and the barium tetraoxosulfate 6, they are prepared by double decomposition. That is, a soluble salt of lead, like lead tetrasulfate 5, is reacted with the soluble salt of tetrasulfate 6 to get lead tetrasulfate 6 as in insoluble form. And let me just give you an example. PbNO3 can be used to prepare PbSO4. You can use K2SO4 aqueous to form PbSO4 solid plus KNO3. So this type of reaction is called double decomposition. So and it is used to prepare insoluble salts. It's used to prepare insoluble salts. So that is that is as regards their preparation. The other thing that you need to know about the salt of tetrasulfuric acid is that they are all stable to heat. Some of them are stable to heat, others are unstable to heat. Those ones that are stable to heat are potassium tetrasulfate 6, sodium tetrasulfate 6, calcium tetrasulfate 6. The 3 of them are stable to heat. When you heat them, they don't get decomposed. Others are decomposed to their oxide, metallic oxide, and sulfur oxide, or metal, sulfur oxide, and oxygen, as the case may be, which we are going to look at in future. Now, the next area where we are going to stop for today because of our time is tests for tetrasulfate 6 salts. Tetrasulfate 6 salts, when they all react with barium chloride to form white precipitate. This is a solution of copper 2 tetraoxosulfate 6. when I add a few drops of barium chloride, we will get a white. This is barium chloride solution. You can see the white precipitate formed is as a result of sulfur tetrasulfate 6 ion in it. Now, how do we confirm that this white precipitate is as a result of tetrasulfate 6? Because it is not only tetrasulfate 6 tetraoxalate 6 ion that forms white precipitate with barium chloride. Trisulfate 4 ion also form white precipitate, and as well as trisulfate 4 ions. So if I add excess dilute hydrochloric acid to it, the white precipitate remains undissolved. That confirms that the white precipitate is as a result of tetraoxosulfate 6 ion. If it is trisulfate 4 ion, the white precipitate will dissolve. If it is trisulfate 4 ion, the white precipitate will also dissolve. But how will I distinguish between trisulfate 4 ion and trisulfate 4 ion? That's also very simple. I just need to get another sample of the solution, and I will test it with an oxidizing agent like acidified tetraoxomanganate 7. You remember last class, trisulfate 4 ion would decolorize acidified tetraoxomanganate 7, acidified KMNO4. It will also turn acidified K to Cl2O7, tetraheptylsodichromate, potassium heptylsodichromate 6 from orange to green. But trisulfate 4 ion will not do this. So that will distinguish the two. So with that, you have mastered again some aspects of salt analysis. Now, let me quickly add this before we come to the end of today's class. You may be required to add a mixture of barium chloride and hydrochloric acid to a sample solution. If you get white precipitate, it shows clearly that it is the solution contains tetraoxosulfate 6 ion, confirmed. Because if it is either of the other two types of ions, the white precipitate would have been dissolved immediately by hydrochloric acid in the mixture. Another way is that if you add hydrochloric acid first before you add barium chloride and white precipitate is formed, it also indicates that the solution contains tetrasulfate 6 ion. No controversy, it's confirmation. So I want to believe that you have mastered today's lesson. Because of our time, we are going to stop here. We'll continue our lesson next time we meet. I pray Allah to grant you understanding of what you have learned. And go and check your portal for the assignments and make sure you do it and submit it as required. Bye-bye. Meet you next time. Assalamu alaikum warahmatullahi wabarakatuh.